again. I apologize about the delay.
No problem. That's the beauty of online tutoring, is that it's
Exactly.
easy to make changes.
Perfect.
So what do you got? You got stuff you can verbalize?
Yes, sir, I do. Okay, so I circled a couple problems that I found to be more difficult. Okay, so the first one is y equals log base 7 and then x squared. Perfect. And then it just says find the derivative of each function. So, the same concept.
All right. Well, y prime.
Okay.
Do you have a textbook or not?
A textbook, I do. We haven't really used it, though, this year. I've never cracked it open ever since this year, though.
All right. I have a textbook that has a great opening page. And it gives you all the derivatives and integrals of common functions. So it would give you the integral or the derivative of this, as u prime over natural log of a times u. In other words, that's the function.
Okay.
And u prime is the derivative of that, whatever the inside is. So what's the derivative of that?
U prime is 2x, right?
Uh-huh.
Okay.
And then over the natural log of 7 times x squared, which is u.
Okay.
Okay? So, notice what that really is. It's the 1 over, in other words, the more common function is natural log of x. What's y prime if y is natural log of x?
Is it using the same format, or
no,
is it?
This is one you want to memorize. This is a key one. This, in fact, might be the most important one in all.
Is the natural log of x 1 over x?
That's it. Memorize that. It's different than all the others, because all the others you can use the power rule, but this you cannot. And in fact, going the other way you cannot. So you need to memorize that relationship.
Okay.
That's not that different than what we have. It's 1 over x times the derivative of x over natural log of a. In other words, if we have something other than natural log, if we have a log base 7, then we're going to divide it by the natural log of 7.
Right.
I hate it that they start on these kind of problems. Now, maybe they didn't. Maybe you picked this because it was difficult. But it's better to start out with problems like this. Excuse me. In other words, if you want to learn how to ski, start on the beginning slopes.
Okay, that makes sense.
Don't start on the difficult slopes. Well, y prime here is 1 over x, and that's one of the most standard things you can learn in calculus.
Okay.
But if y is the log something other than e, then y prime is 1 over natural log of 7 times x.
Okay.
That's the only difference.
Okay, that makes sense.
Basically 1 over x, but there's that natural log of the base. Now, if it was natural log of x, then it would be natural log of e, which is 1.
Right.
All right.
Okay.
What else you got?
Okay, so the next one would be y equals ln cubed parenthesis x squared.
All right. This is a chain rule.
Okay.
What's the first part?
You bring the 3 to the front of the ln, so it's 3ln squared. Then x squared, tack that on, and then do you multiply it by the derivative of the inside?
Yeah, you do.
Okay, so that would be 2x.
Let me think about this for a second.
Okay.
I want to write this in terms of u substitution. I think I got to apply the chain rule twice.
Okay.
In other words, it's equal to u squared of v. Correct?
Okay. Right.
Excuse me, u cubed.
Okay.
So if I were to take the power rule on that, I would get 3u squared of v times
Right.
dv dx.
Right.
Well, there's my 3u squared of v, but I haven't taken dv dx.
Right.
Think this is a double application of the chain rule,
Okay.
which is hard to understand. Let's go through it. I'm going to
Okay.
say that u equals natural log of v.
Okay.
So our function really is u cubed of v.
Okay.
With me?
Yes.
If I take y prime, then it's 3u squared times dv dx.
Okay.
Well, that becomes 3 natural log of x squared. That's what v is.
Okay.
Squared. In other words, 3u squared becomes 3 natural log of x squared times dv dx, which is 2x.
Okay.
So I think that's the answer. Let me look at it again. This is whenever you have a double application of the chain rule.
Yeah.
Let's go through exactly how we're going to do this, because these are the only tough ones. I have no doubts that any single application of the chain rule you're going to be able to deal with just fine.
Right.
So let's deal with double applications.
Okay.
I'm going to start from scratch here,
Perfect.
just so we know exactly what's going on.
Okay.
First of all, I'm going to let u equal natural log of x,
Okay.
which means I have y equal u cubed of x squared.
Okay.
Now, du dx over here on the right is 1 over x. And I know I have to multiply this by du dx.
Okay. Okay. So then.
So I get u cubed, which is natural log cubed of x. Hold on a second. Just a second. Just a second. Y prime is 3u squared of x squared times du dx, which is that.
Okay.
So
That makes
if
sense.
I put this into the format that I can tell, this is what I've got. You with me?
Okay, ln squared x. I just don't know where the second x came up from following the ln squared and then the parenthesis x squared.
Yeah.
That's where I'm at.
Okay. Trying to think of how to explain this.
ln x.
First of
Because,
all,
oh wait.
notice what u is. U is not x squared. We got two insides here. I'm going to call one of them u. I'm going to call one of them v.
Okay.
Okay? So,
Oh,
u
okay.
is
That
the
makes
natural
sense.
log of x. That's the first inside.
Okay.
So if I use u as the natural log of x, then I got 3u squared of x squared
Right.
times the derivative of du dx, which is that.
Right.
Okay. Now, I also have to apply the second application of the chain rule, which is the derivative of the inside, the second inside,
Okay.
which is that. Now I should be able to combine it all. So y prime
Okay.
equals 3. U is natural log squared of x squared times 1 over x times 2 over x. That's times 2. So my final answer should be this at the bottom.
Okay. 6.
Do you have answers for these, Max?
I do. Yes, I do.
Good. Check that. See if that's right.
We go and double check. I got y prime equals 3 ln x squared,
Hold on.
or 3 parenthesis ln x squared.
ln.
Okay, so it'll be 3 parenthesis ln x squared.
All squared, right?
All squared, and then times 2 over x. Now that's what they taught me at Sylvan. That's what I got there. And I believe I do have a key that my teacher
Well, notice
has.
that that's not that different than what we got.
Okay.
In fact, the 2 over here multiplies the 3 over there to give us our 6.
Okay.
This term, natural log of x squared squared, is the same as that term.
Natural log of, oh, that makes sense. Okay. Because it's, oh, that, okay, yeah, it's just rewritten differently.
In other words, natural log of x quantity squared is equal to the natural log squared of x.
Squared of x. Yeah, perfect.
So the only thing that's missing is that denominator. How did I get one less x in there? Because the way I did it, that x canceled with that x.
And I don't know if the Sylvan person picked up on that either.
Okay.
That's what I think.
When calculus is tough, Max. Every problem usually has about 12 steps to it, and by the time you reach the final answer, if it's not the answer in the book, you say, well, which of the 12 steps did I make a mistake on?
Right,
and
exactly.
You can choose one of two options, to go back to the beginning and work it from the scratch.
Right.
Or Just assume that I made a mathematical error and go on to the next problem. And I honestly think that it's in your best interest to go on to the next problem.
That's what I think it is
How I
too.
ended up with one too few x's in the denominator, but that's
Yeah.
the difference between my answer and your answer.
And what it seems to me too is the way you have it set out is a much more comparable to the way my teacher does her work when she does the keys.
Okay.
So I feel as if the woman at Sylvan just messed up on a step. I feel like what you and
Well,
me
it's
just
pretty easy to mess up on a step. You can see.
exactly. That's what I'm saying. Yeah, it's there's so much room for error, you
Yeah,
know?
there is. You just can't
Yeah.
make one mistake or you're going to get the wrong answer.
Exactly. That makes sense.
Especially with a dual application of the chain rule.
Yeah.
Let's talk about that for a second.
Okay.
Definitely going to let you, and this is the best way to learn the chain rule, is figure out what you're going to let u be.
Okay.
Now the reason I'm going to let u be that is because then y is equal to u cubed.
Okay. Oh, okay, that makes sense. Yep, I get that.
Okay. Then I have another application of the chain rule. And let's call that v. Well,
Okay.
v is going to be equal to x squared.
Right.
So when you have a dual application of the chain rule, probably the best way to treat it is with different letters. You got a u, a v. I haven't seen very many problems where you have to apply it 3 times, but if you did, then the x one might be y or z.
Yeah.
Okay? So if I use this, then y prime is u cubed of x squared.
Okay.
Now, if somebody gave you this problem right there, and they said differentiate, no, excuse me, my apologies, y is equal to that, not y prime.
Right.
Okay?
Okay.
Now, if somebody gave you this problem and they said differentiate it, well, you would immediately say, well, that's 3u squared of x squared times the derivative of the inside, which is 2x.
Right.
Then you would go back in and substitute. So that's u isn't u, it's natural log of x squared.
Right.
So natural log of x squared squared
Right.
times 2 of x.
Okay.
And what that seems to me like it should be, hold on.
6x ln squared of x squared.
Yeah.
That all makes sense to me.
And that is the answer I believe I came up with originally.
That is. Yeah, that is.
And that squared there I can put there.
Yeah, exactly. Yep.
So I think that's the answer.
I think that's the answer too.
Now,
That makes so much
they
more.
ended up with an extra x in the denominator.
Yeah.
And I don't know. You know, these are
They're
difficult
tough.
at best.
Exactly.
So probably the best thing we can do is go on and try another one.
Perfect. Okay, so the next one that I have is y equals log base 5 parenthesis. Okay, so it's a big parenthesis, and then this is a fraction. This is all in the numerator first of all. X squared, and then the square root of 3x plus 1. And then that's all over x minus 2 in parentheses to the power of 4.
Okay. Well, first of all, let's start with this. What's y prime equal to if y is equal to the log base b of u?
Y prime equals u log b.
Well, it's equal to u prime. Well, in fact, let's start. I don't want to even write it like that because it's the log of the outside times the log of the inside. Excuse me. It's the derivative of the outside times the derivative of the inside.
Okay.
The derivative of the outside is 1 over u, but it's times the natural log of b.
Right.
And then the derivative of the inside is times u prime. So what that gives you is u prime over natural log of b times u.
Okay. Natural log.
That's what y prime is.
Okay.
Now, why they gave us such a complicated one, I'm not sure.
But that's the simple format that you're supposed to follow.
Right, that's the format. In other words, I have a calculus book that if you open the inside page, it gives you all the standard derivatives and integrals.
Okay.
I haven't got to integrals yet, but it's nice having a table of formulas for derivatives.
Yeah, exactly. Exactly. That makes sense.
Yeah. So let's fill in everything.
Okay.
Y prime equals 1 over natural log of 5
times the big fraction, right?
Yeah, we'll just label it u, save myself writing,
Exactly.
times u prime.
And then u prime's a
Let's
quotient
let
rule.
u, let me spell out what u is here.
Okay.
X squared times that all over x minus 2 to the 4th, correct?
Yes, sir.
Wow, why would they make this so complicated? It makes me think that I'm missing something. Let me think about this for a second. Well, we know we need u prime. At some point, we need u prime, right?
Yes.
Let's get u prime. What do we have to use?
Quotient rule.
Complicated function using the quotient rule. All right.
So you're gonna have to convert it like the 3x plus 1. That's gonna have to be converted into like an exponent. No.
Right.
And then it's almost like a product rule in the numerator inside
It's
of a
horrible. I mean, this problem alone would be challenging. So
but I mean,
write it.
Let's
write it the way you want to write it.
Right. Now, don't get me wrong. Like, it's a lot of work, but given the fact that I know what steps to take to solve the derivative of that.
Okay. So you can figure out what u prime is based on u.
Right. Right. Exactly.
Okay.
I know what needs to happen.
So we'll call u prime equal to z.
Okay.
So we get y prime equals 1 over natural log of 5, which is just a number,
Right.
of, why would they give you this problem? I don't get it.
I don't get it either.
What's the advantage of giving you this problem? I mean, I can't imagine a problem that's more complicated, hardly.
Really?
Well, really, yeah. So there's 1 over natural log of 5 times u.
And all of that.
The derivative of u, which we're calling z.
Exactly.
So that's going to be your answer, and whether it can be simplified or not, oh my God, I mean, First of
Okay.
all, figuring u prime is a nightmare
Right.
because it's the bottom times the derivative of the top, which involves the product rule and the chain rule, all over the bottom squared. So u prime is going to be a hugely complicated number.
Right.
Are you sure this is something they expected you to figure out by hand, or is this possibly something they wanted you to put in a calculator?
Right now it says this on the piece of paper that you gave me. It says put all work on a separate sheet of paper. That's what it says.
Well, she should have said put all work on 5 separate sheets of paper.
That's what I'm saying, you know. But like with this said, I mean, I feel like if anything, this is all just a big review. That could have just been a question that she just threw on there and was like, all right, this will test these rules for them. Let's see if they can.
Well, it's definitely a big algebra problem. That's what it is. It's an algebra problem.
Huge algebra problem, yeah.
You know what? That's what a lot of calculus is. In other words, the most important skill you can have for calculus is algebra skill.
Yeah.
Seriously. Reducing some of these quotients that you come up with is an exercise in college or algebra 4 almost.
Uh-huh. I believe that.
Just because you have such complicated quotients.
Uh-huh.
And you end up having to factor stuff out, simplify. It's amazing. Yeah. And sometimes you can get these super complicated expressions and they simplify to the number 2 or something.
Right. Exactly. Like, and it's like you do all this work and you get a simple answer.
Right. Right.
You know? And you're like, how can something like that be derived down to something so little? But
right. Well, I kind of get that, but it's a giant algebra problem.
Yeah.
Now, you want to get even worse? Start taking second derivatives.
Oh, yeah, that's even. I've taken double derivatives of, like, graphs and stuff like that.
Notice that the first derivative of that is a nightmare. Imagine what the second derivative is going to be. First of all, you're going to have x minus 2 to the 8th. I mean, it's just, the complexity is exponential, or maybe I should even say factorial. In other words, it grows about as fast every time you take an extra derivative, or if you have a quotient rule involved, well then taking derivatives is super tough.
Exactly.
But the key step here is not the algebra. The key step here is to recognize that that is you.
Uh-huh.
And then once that becomes, I guess that's you, yeah. Once that becomes you, then to solve for u prime, that's a lot of work. If I just gave you y is equal to that function and solve for y prime, my God, that'd be a 20-minute problem.
Exactly.
So I'm trying to figure out why he's giving you this problem, where the inside is a 20-minute problem. That involves more knowledge, and then simplifying the whole thing at the end is probably another 20-minute problem. So if he gives you this problem on a test, he better not have very many other problems.
I know, right? Yeah. That will not be on a test. I highly doubt it.
I wouldn't think so. I wouldn't think so. This is about as hard as it gets in terms of complex algebra. It's not hard in other respects.
Right.
In other words, it's the log base 5 of u. And then figuring out u, that derivative involves, gosh, quotient rule, the product rule, and the chain rule.
Exactly.
So that's tough.
It is ridiculous. Yeah.
And I mean, it just gets, I don't quite understand why teachers do this.
Yeah, and I don't really find a reason for us to be stressing too much over that problem either. There's plenty of...
This problem doesn't really demonstrate much. It just demonstrates how complex some of these functions can get.
Exactly.
It doesn't,
doing all the same thing.
Demonstrate knowledge. It just maybe demonstrates terrific algebra ability.
Yeah, and organization skills and stuff like
Well,
that,
for
you know.
sure that, but if nothing, calculus is all about organization skills. In
Right.
other words, the one thing you want to do for sure on calculus is go from row 1 to row 2 to row 3 to row 4. And
Right.
in fact, funny story, when I first started tutoring calculus, which was probably 6 years ago,
Okay.
I switched from letter size paper to legal size paper.
Okay.
8 by 11 to 8 by 14. And the reason I did it is because calculus problems took an 8 by 14 sheet of paper to solve normally.
Exactly.
8 by 11 wasn't big enough. Not
No.
the size of writing that I use, which, you know, I like to at least be able to read it, but I really want everybody else to be able to read it. So
Right.
calculus problems have an unbelievable amount of steps in them. And if there's one thing I've learned on a calculus problem is you should start in the upper left-hand corner, which you'll notice I didn't do here. I started
Yep.
in the top, but I should have started over here.
Okay.
Because you're always going to need the room. You're going to need the space.
That makes sense. Okay. Okay, I get that.
All right, what else you got? Let's go on. Probably is the best thing to do.
Okay, so the next one I have y equals ln parenthesis ln sine 3x.
They're really trying to test you.
Oh no.
So, on a problem like this, I think the best thing to do is to define u as the starting spot.
Okay.
What's u?
ln x?
No?
Or is it
I would say it's this.
ln the sine 3 of x? Okay.
Yeah.
That makes
The reason is that we want to convert this into y equals natural log of u.
Right.
Why? Because if I have this, then I know y prime is equal to 1 over u times u prime, just using the chain rule.
Right.
Okay? So I know what u is. I'm going to go up here on the upper right and figure out what u prime is. What's u prime?
U prime is going to be 1 over cosine 3x.
Actually, it's 1 over sine 3x
Sine 3x.
times the derivative of that.
God, which is cosine 3x. Okay.
Not quite. We got a fourth application of the chain rule. What's the derivative of that inside?
Oh, 3. Okay.
So that's what u prime is.
Okay.
So my answer is going to be 1 over natural log of sine of 3x
Okay.
times u prime times 3 cosine of 3x over sine of 3x. That's u prime.
Okay, 3 cosine 3x over sine 3x. That makes sense.
Now, notice that u prime required a double application of the chain rule.
I did notice that, yeah.
Yeah, it's 1 over this u. Now, it's difficult to use u substitution when you have multiple applications of the chain rule. So sometimes I'll use just different letters. In this case, v would be sine of 3x. So I would have u equals natural log of v, which is u prime is 1 over v times v prime.
That makes sense. Okay, I see.
That's what we got. There's 1 over v, well, and then v prime is that.
Right.
So this might be one of the few applications I've ever seen where there appear to be 3 chain rules.
Okay.
It's the derivative of the outside times the derivative of the inside times the derivative of that inside times the derivative of that inside.
Okay.
So
Okay.
4 chain rules. I've never seen a problem that had 4 chain rule applications. But this is one of them. And
I see it though, and it's simple. It's complex. I mean, I understand where you're coming from.
probably the best way to view these is to start out with U.
Yeah.
And then
Yeah.
treat each problem like a separate problem.
Exactly.
If U was this, then what would U prime be? Then you would have a triple application of the chain rule.
Right.
But eventually you get U prime.
Exactly.
And then you just multiply 1 over U times U prime. And now, whether I can simplify that or not, I don't think so.
I don't think so. You can just like combine the fractions, I guess, but
Yeah, I could make that cotangent of 3x. So
yeah,
you know, because cosine of 3x over sine of 3x is 3 cotangent of x.
That makes sense.
So I could do that. And then I have it over the natural log of sine of 3x. I think this is probably the answer that you'd find in the back of the book if they gave you answers.
Okay. Now, correct me if I'm wrong. Would it be cotangent of 3x, or would it just be cotangent?
Sorry.
Okay. So it would be, okay, I just want to make sure.
Yep. My mistake.
No worries. Okay, 3 cotangent.
One of the problems with calculus is you cannot make a single mistake.
Right, and there's so much room for error. Exactly, that makes sense. And there's so much room for error too. It's kind of tough.
Because the average problem they're giving you has like 12 steps to it.
Yeah.
So you got to be 95% correct to get the right answer on every step.
Okay, that makes sense.
Now, I can't do anything with the bottom. You might think that the reciprocal of sine is cosecant, so I could put it in the top, but I really can't because it's natural log of sine of 3x.
Okay, that makes sense.
Because normally they don't like trig functions in the bottom.
Okay.
And if you have an answer that's got a trig function at the bottom, you should use the reciprocal and put it in the numerator. But this is the natural log of a trig function, which is not as easily converted and put in the numerator.
Okay. Okay, that makes sense. So, like, let's say it was just like sine of 3x.
You got an answer like this.
Yeah, I could do like 1.
Yeah, you would never want to give that as an answer. That is cosecant of x.
Right. Okay, that makes sense. Okay, perfect. Okay, so then I have one other derivative problem, and then we're going to go down to like the tangent lines and stuff like that. But this last one is y equals cosine parenthesis x squared minus pi over 4. That's it. U is x squared minus pi over 4.
We know we're going to need u prime.
Right.
Prime.
U prime is going to be 2x, right? Because the pi over 4 just omits itself, right?
Right. So our problem is really cosine of u, and y prime is going to be sine of u, negative sine of u times u prime.
Okay.
Because the derivative of the outside, which is minus sine of u, times the derivative of the inside.
So then, like, convert it all, like, transfer it, simplify it a little bit. So then,
put it negative back in terms of x.
Right. X squared minus pi over 4. So would the final answer be y prime equals negative 2x sine parenthesis x squared minus pi over 4?
Yes.
Perfect. That's pretty straightforward. That one was very simple. I just want to kind of brush up on that. We haven't gone over those in a little while.
I don't think that can be simplified.
Yeah. I don't think that is. That is the answer that I got with Sylvan, and also I would assume that is the same answer that she put on her key.
All right.
So.
Yeah,
Okay.
that was just one application of the chain rule.
Right.
Which are generally pretty easy. It's when you get 4 applications that you got to be careful.
Exactly. It gets kind of confusing, and you make sure you do it in the right order.
Right.
Okay. So then now for this next one, it says give x values at which the tangent line or line are vertical of x squared minus xy plus y squared equals 9.
So they want where the tangent lines of this function are vertical.
The x values at which the tangent line or lines are vertical. Yes.
Okay. Whatever this function looks like, and it could be, we'll pretend it's an ellipse. I don't think it is. But what they're asking for is what's the x value of that and the x value of that.
Okay.
Well, where the tangent lines are vertical is where the first derivative is undefined.
Okay.
So we're going to want to solve this for dy dx.
Okay.
And set that equal to undefined and figure out where we have division by 0, which is always where it's undefined.
Okay.
So implicitly differentiate that. In other words, take the derivative of that with respect to x and the derivative of that with respect to x.
Okay, and that 9 is just going to cancel out.
What's that?
Okay. Isn't that 9 just going to cancel out into 0?
It is. That goes to 0, okay.
So then it'll be 2x minus, and then it's like x derivative of y times y derivative of x. So it'd be like xy prime times y, or plus y. It would be xy prime plus y because the derivative of x is just 1.
Correct. Notice that the most important part of this is making sure I put parentheses around it.
Right, right. Make sure that they're all together.
If I do not, if I leave out these parentheses, I'm going to get the sign on this y term wrong.
Okay. That's good to know. Perfect.
So I am subtracting that.
Right.
The derivative of that. And the derivative of that is xy prime plus yx prime.
Right.
Okay.
Which is x y prime plus
y. So just put it in parentheses for now. And what's this final term's derivative?
That one is 2y, and then you don't have to follow it up with a y prime for that one, right? Or do you?
Yes, you do.
Okay.
In other words, here's the rules. When you are implicitly differentiating,
yeah,
and you come across a variable different than this variable,
you
have to follow it with dy, that variable. In other words, if I had to come across an r, then I would have had to follow it with a dr dx. If I had to come across a t, I would have had to follow it with a dt dx.
Okay.
Anything other than x, you would have to follow with d of that variable with respect to x. You can even think about it as even follow the x with a dx dx.
Okay.
Because that's 1, so that always goes away.
Right.
So the really way to think about this is every time you come across a variable, explicitly differentiate it and follow it with d of this variable relative to dx.
Okay.
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 Now, all of that is equal to 0.
Right.
The right side went to 0.
Okay.
Now, the way we're going to solve this for dy dx is we're going to move everything that does not have a dy dx to the other side.
Okay.
But first we probably need to distribute this. So I've got 2x squared y prime, you're comfortable with that, plus 2xy minus 2y y prime equals 0. You with me?
Yes.
Okay. Well, now I'm trying to solve for y prime. So every term that has a y prime in it, I'm going to keep on the left side, and every term that does not have a y prime in it, I'm going to move to the other side. So now I have this. Now it's a factoring problem.
Right.
These are difficult until you figure out how to do all of them, and then they're always the same. You factor out y prime, leaving behind 2x squared minus 2y equals minus 2xy. Now you divide by that coefficient.
Right.
So you get y prime equals minus 2xy divided by 2x squared minus 2y. You can certainly divide top and bottom by 2.
Okay.
That's what you get. There's your answer. Now, what's different about implicit differentiation is that you frequently get your answers in terms of x and y, not just x. When you explicitly differentiate something, you always get an answer in terms of x and x only.
Right.
But when you implicitly differentiate something, you get an answer frequently in terms of x and y.
Okay.
Okay? And that's fine, because usually follow-up questions might be, come up with the equation of the tangent line, but they would give you at 3 comma 4. They're not going to give you just the x coordinate. They're going to say, what's the equation of the tangent line at 3 comma 4? Well, that means that y prime equals, you plug in the x coordinate and the y coordinate. So I can figure out the slope at that line.
Right, and then you plug it into like the y minus y equals slope.
In other words, the slope at 3 comma 4 is equal to minus 3 times 4 all over 9 minus 4. So what's that equal to? Minus 12 fifths.
Okay, and that's the slope.
My slope. That's what y prime is the slope of this relation at that point. So if I want to find the equation of the tangent line, in calculus, the best thing to use is always point slope, because that's usually what you have, is one point and one slope.
Right.
Well, I've solved for slope, and there's my point. So the equation of the tangent line would be this. Excuse me.
That makes sense. Okay.
And with calculus, that's always the, if somebody's going to test you on calculus and they're only going to give you one question, it's always going to be, give me the equation of the tangent line.
Okay.
That's the most, that's the quintessential question in differential calculus, is give me the equation of the tangent line, I will give you the function and the point. And you tell me what the equation of the tangent line is that goes through that point. In other words, graphically, maybe that thing was an ellipse.
Yeah.
And I want the equation of the tangent line at 3 comma 4. Well, there's 3 comma 4. So I want the equation of that tangent line.
Right.
It's going to
Okay.
have a certain slope, and it's going to go through a point. And once you have
Right.
a slope and a point, then you can always use point-slope format to figure out the equation of that line.
Perfect. So then when it says give the x values at which the tangent lines are vertical,
Okay.
that would mean
Yeah,
y.
let's go back and look at that. I forgot about that part of the question.
Okay.
Hold on. So we got
So yeah, that y prime part. There we go.
so here's y prime.
Mm-hmm.
Where is the y prime going to be vertical?
When the slope is at 1, right?
No, when the slope is at infinity. In
Infinity.
other words,
Okay.
where this denominator is equal to 0.
Okay.
So I'm going to say, where is x squared minus y equal to 0? Well, that's x squared equal y. Where is that equal to 0? Well, there's not very many values. X could be 0. X could be 1. I think that's it.
Okay.
In other words, x is equal to, the only way that equation could be true is if x is 0 and y is 0, or x is 1 and y is 1.
Okay.
No other
Okay.
number. If x is minus 1, y is plus 1. But the only
Okay.
place where x squared minus y is equal to 0 is at x equals 0 or x equal 1.
Okay. Okay. That makes sense. So if it's ever asking for where the x values, or asking for the
Vertical
x values,
slopes.
which the
Vertical
line is
slopes are
vertical,
tough. You have
yeah,
to make the denominator 0, which is
that's
good for any mathematician to do, because from second grade you're taught that you cannot divide by 0.
right.
So it's difficult when you have a problem where you have to make the denominator 0. That's where
Right.
that slope is vertical, is where the slope of the tangent line is infinite. And it is
Oh, okay.
infinite only when the denominator is 0.
That makes sense. Perfect. That's good to know. I did not know that. Okay. So then next question. This says, okay, so for 5, there's 2 problems. There's like 5A and 5B.
Okay?
Now, for both of those problems, it wants us to give the f of x, or the derivative, and then the derivative chart, and then the double derivative chart, the relative max and mins, and points of inflection as ordered pairs. You have to sketch a graph and then label all key points.
I know exactly what they're talking about. Whether we can do it in 8 minutes or not, I don't know, but let's give it a shot.
Okay.
Unfortunately, I have a 3 o'clock appointment, so I can't go beyond 3. But
Perfect. No worries.
what's f of that?
So the first one, it says y equals 3x to the 5th minus 20x cubed.
Now, since they've asked about first derivative and second derivative, let's just go ahead and find out what those are.
Okay. So the first derivative is going to be 15x to the 4th minus 60x squared. And then the double derivative is going to be 60x cubed minus 120x.
Okay.
Okay.
Now, read the problem again for me.
And then it says, so after we find the derivative and the double derivative, it wants the derivative chart and the double derivative chart.
Okay, let's stop there for a moment.
Okay.
Let's go down to the derivative chart.
Okay.
Now, this you'll notice can be factored.
Okay.
That's 15x squared times x squared minus 4, which is actually 15x squared times x minus 2 times x plus 2.
Okay.
What are my critical points on the derivative chart?
0, +2, and -2.
Now, what's useful to know is where the first derivative is negative and where it's positive.
Okay.
Because where it's negative, the original function is going to be decreasing.
Okay.
Where the first derivative is positive, the original function is going to be increasing.
Okay.
And those are very useful things to know. So when they
Right.
talk about a first derivative chart, they want us to know where this is plus and where it's minus.
Okay.
The way you figure that out is you pick a number to the left of your, I've labeled the 3 critical points. And I didn't put 0 on there just because it's 0. I put it on there because it's a critical point.
Right, right.
Only that. I'm only putting my 3 critical points on here.
Okay.
So pick a number to the left of minus 2. Is that
-3.
positive or negative? Okay, so that part's positive. -3, that's part's negative, and that part's negative. You
That's
don't
gonna be
need to know the numbers. You just need to know whether it's positive or negative.
And that's going to be positive, correct?
So everywhere left of -2, I get that.
Okay.
Now pick a number between -2 and 0.
Give 1.
And at -1, that's positive. What's the middle term?
Negative, and then positive again.
So now that product is negative.
Right.
And what that tells us is that every x value between -2 and 0 is going to produce a negative f of x, or f prime of x in this case.
Okay.
Now pick a number between 0 and 2.
1. Positive.
That's positive. What's this?
So that's going to be negative, or that's, yeah, negative and then positive. So that's going to be negative overall again.
Finally, number greater than 2.
Right. So that's positive. 3 minus 2 is positive. 3 plus 2 is positive. That's all positive.
Okay. So there's your solution chart as to where f prime of x is greater than 0 and where it's less than 0.
Okay.
In other
And
words,
then
less than 0 there.
Okay.
And it's greater than 0 whenever x is less than -2 or greater than +2.
Okay. Okay, that makes sense. So then when it says a relative max and min, do I use
We need the line chart of the second derivative.
Okay.
So factor the second derivative.
I can take a 60x out, which would just leave me with an x squared. So 60x, x squared minus 2.
Which is 60x times x minus square root of 2 times x plus square root of 2.
Okay.
In other words, you don't need that to be difference of perfect squares. That's what they teach you when you first learn algebra.
Right.
The fact is, it's just got to be difference of squares, and square root of 2 is a good number, so I can still factor that. And it gives me my critical points. Again, I have a critical point at 0 for that one.
Yeah.
I have a critical point at square root of 2, and I have a critical point at minus square root of 2.
Okay.
So if I do a line chart for the second derivative, trying to figure out where it's positive, where it's negative, I'm going to use the same process. Pick a number to the left of this. About
-2.
-2.
Perfect.
Well, that would give you minus, minus, minus. So those those are minuses.
Okay, that makes
Pick
sense.
a number between 0 and -2. How about -1?
Yes, sir.
That's minus,
Minus
minus,
plus.
plus. So that's plus. Pick a number between 0 and √2, like
1.
1. That's plus, minus, plus. So that's also, no, that's minus. Right?
And then say 2, right.
And
then
pick a number greater than that, like 2, and you got plus, plus, plus.
plus. Okay.
So there's the line chart for the second derivative.
Okay.
Now, go back and read the problem again, starting
And then it's
near the beginning.
and then it asks for a relative max and min and points of
Okay.
inflection and
Stop.
ordered pairs.
Stop for a moment.
Okay.
Relative max and mins. If I have a function that's like that,
Right.
well, that is a relative maximum because my slopes go from plus, plus, plus to minus, minus, minus.
Perfect.
So right there is a relative maximum.
Okay.
On the minimums, they go from minus, minus, minus to plus, plus, plus. So right there is a minimum.
And then a point of inflection is where the sign doesn't change at all, right?
Point of inflection is where the second derivative is 0.
Okay. Okay.
Where is the second derivative 0? At x equals 0 and x equal square root of 2, plus or minus square root of 2. So, in other words, I'm looking at this function here, my second derivative function.
Right.
Zeros of that are x equals 0 and x equal plus or minus square root of 2.
Okay.
So we should have 3 inflection points.
Okay.
Inflection points are always where your second derivative is equal to 0.
Okay.
And you can kind of see on my second derivative curve that it goes from minus to plus right there.
Right.
It goes from
Plus to
minus to
minus.
plus right there, and it goes from plus to minus right there. Those are those 3 numbers.
Okay. So those are the points of inflection. I see.
Those are the points of inflection. Exactly.
Okay.
What else did
And you write them as ordered pairs, but that's just basically like those are all x values, right?
Yes.
Okay, so then yeah, perfect. And then it says sketch a
Well,
graph and
this is
walk.
important. Hold on, let me cover something here.
Okay.
These are the x values. If you want the f of x values, you got to go all the way back to the original function.
Okay.
In other words, if you want the coordinate pairs, I'm going to plug in plus and minus square root of 2 for x.
Okay.
In the original function. Remember what all of these derivatives are kind of inclined to want to do, and that is to be able to graph the original function. In other words, a lot of times you'll get a problem where they will not give you the original function, but they'll give you the first derivative function.
Okay.
And from that first derivative function, you can basically graph the original function. Trust me, you can. You can graph it within reason.
Right.
You can't necessarily graph it on the y-axis, but you can graph it on the xy plane, and you'll get a graph that's like this, and it could also be like that, or it could also be like that, or it could also be like that, but it's one of those graphs.
Okay.
So from the first derivative function, you can graph the original function, or almost graph the original function.
And now when so with me trying to graph the original function off the derivative, don't I basically do the opposite of what the derivative is telling me to do?
Well,
or does the derivative tell me how the actual graph flows?
Let's see how we would do it here.
Okay.
here's going to be the original function over here on the left.
Right.
First of all, what are the zeros of that function?
The zeros
That's
of the
a good starting spot, right?
Right.
It tells me where it's going to cross the x-axis.
Right.
Well, there's certainly one at 0.
-2 and +2, right?
Well, let's see. If I factor out a x cubed, I get 3x squared minus 20. So I've got 3 zeros at x equals 0, and I have 2 zeros at plus or minus square root of 20 over 3.
Oh, okay.
In other words, solving that for 0 gives me plus square root of 20 over 3 and minus square root of 20 over 3.
Okay.
So those are my 3 zeros. So I know I got to go through the function there.
Okay.
Now, if I look at my first derivative, when the first derivative is 0, which is at 0, 2, and minus 2, then my original function must have a flat horizontal tangent line. So I got a horizontal tangent line there. I got a horizontal tangent line there. I got a horizontal tangent line here.
Okay.
And that's all I know at the moment. Now, if I look at my second derivative, let's go back and look at the first derivative.
Okay.
The first derivative to the left of minus 2, first derivative is positive.
Okay.
That means my original function is increasing.
Okay.
So my original function must be increasing up to 1 or minus 2.
Okay.
I know it goes through that point where I've got the x, and I know that it's increasing up to minus 2 because the first derivative is positive based on that.
Okay.
And then the first derivative is negative, which means the function has to be decreasing between minus 2 and 0.
Okay.
And I know that at minus 2, the derivative is 0.
Okay.
So the first part of the graph looks pretty good.
Right.
Now, from 0 to minus 2, the first derivative is negative, meaning the original function has to be decreasing.
Okay.
I also know that at 2, it's 0.
Mhm.
And then from 2 to infinity, it's increasing.
Okay.
So it looks like it could be that curve. Now let's check our second derivatives. Second derivative is 0 at root 2. Well, notice that it would be. In other words, what I've drawn here is the first derivative curve. So always remember the second derivative curve is the derivative of the first derivative.
Okay.
Max, I'm really apologize. I just looked at the time. It's 3:08. I am 8 minutes late for my next appointment.
I apologize about that. Thank you so much. You've cleared up so much.
No problem. And I will see you at Highlands Ranch Library on Friday.
Perfect. Sounds good. Thank you so much. Enjoy your day.
All right. You too.